Good afternoon, class. This is on Chapter 8. We're in Chapter 8 now. And Chapter 8 revolves around several major things, but one is torque, another one is angular rotation, and another thing is called angular momentum. So torque, as it turns out, you're probably familiar with it because if you ever had a flat tire, you had to use a lug wrench to take off the lugs. You apply a force at the end of the wrench and it causes a rotation. There's an old saying, you've all heard of it, lefty loosey, loosen the lug, righty tighty to tighten the lug. So torque involves really three things here. One is a force, another one is a radial distance, another thing is the angle. So I'm going to demonstrate that with this wheel right here, but there's no torque wrench. I'm going to use my hand to apply the force. The force is applied at this distance right here. That's the radius of the wheel, and it'll cause the wheel to rotate. Now once it's rotating, what will happen is it'll go at a constant speed, but while it's speeding up or slowing down, it will accelerate. So I'm going to apply a counter torque to slow the wheel down, like that. So it's decelerating at that point, but if I apply the force again in this direction, then it causes an acceleration. And it'll accelerate to reach a constant speed, then it will continue on as inertia until it eventually slow down. But in this case, I'm going to apply the counter torque and cause a deceleration right here. Now, in order to show you this, I need a little stick, I guess, or maybe just my finger would be good enough for this. Because I wrote this on the whiteboard here. Oh, here's my stick. The torque causes rotation. Now also you're going to have some JPEGs, videos of this sort of thing. But it's in the textbook, pages 8-1 and 8-2 of the textbook. The torque, which is usually represented by the symbol tau, T-A-U, tau, Greek letter tau. And this should say tends to cause, where it should be T-E-N-D-S, to cause rotation. And you want me to fix it now? My
Yes.
assistant is saying fix it. Okay, so we'll do that. Like I keep saying to my class all these years, I can't be perfect for my wife, so I definitely can't be perfect for you. So the torque tends to cause rotation. Torque will be the radius, the distance, right here in this diagram, times the force, and the angle here is 90 degrees. In our class, it's always going to be 90 degrees. It'll make it easier for you, because the sine of 90 degrees is equal to 1. And so it's going to be the radius times the force, but now the force is equal to m times a, causes acceleration. So this will be, torque will be r times ma, but in the case of this angular acceleration, that's given by this equation right here. The acceleration is equal to the radius of the radius times the angular acceleration, and that letter is alpha, Greek letter alpha. So I put that in here, like this, now. And now we have r times r, that would be r squared. And this could be written as mr squared times alpha, where mr squared stands for the moment of inertia. It's called the moment of inertia, or the rotational inertia. So all objects which rotate have a tendency to resist rotation, mr squared. Now it also depends on the shape of the object. And this simple wheel I have right here, that's pretty close to the exact value. But if we have a sphere, like a bowling ball, then we have a different formula for that. We'll get to that a little bit later. For the sphere, it would be about 2/5 mr squared, about 0.4 mr squared. But I'll write that down again later. If it's a solid disk, then it comes out to be about 0.5 mr squared. And you get this formulas by using something called calculus. So we're not going to bother doing that for this class, but that's where it's coming from. Now after this, we have to move on to the next section about angular acceleration and the quantities which are involved in that. So that's the next board right here. Now in this case right here, I draw a circle. There's the radius right there, and this is called the arc length. And if the arc length is equal to the radius, then we have an angle which is 1 radian. 1 radian. Theta would be equal to 1 radian, which is about 57.3 degrees. S equals R, then theta will be equal to 1 radian, which is about 57.3 degrees. Now, we haven't had to use radian before. The radian is a dimensionless quantity. Doesn't usually get into the final answers of the problems, but it's something which is very useful in Chapter 8. Now, if we go back to Chapter 5, you might remember this formula. For an object going in a circle, once around the circle is 2 pi r. That's the circumference of the circle, 2 pi r. The tiny ground once is called the period. So you have to remember from Chapter 5 that particular formula. Well, right here, though, this 2 pi divided by t, now in Chapter 8, we're going to be calling that omega. Omega is the angular velocity. And the angular velocity is equal to 2 pi divided by t. And in Chapter 8 now, instead of v equals 2 pi r over t, we're going to be referring to the velocity as the radius times the angular velocity. V is equal to r times omega. And also in Chapter 8 now, acceleration is going to be equal to r, the radius, times the angular acceleration. Angular acceleration is alpha. Now going back to Chapter 2, history is repeating itself. We have to deal with the formulas from Chapter 2. For linear motion, if you recall, if a car traveling at a certain original speed is accelerated in a certain amount of time, it'll give you a final speed v. The distance, if you remember from Chapter 2, the distance is equal to v sub 0 t plus 1/2 a t squared. And finally, this one is from Chapter 2, v squared equals v sub 0 squared plus 2a, and this would be x minus x sub 0. So that's a mistake that I made here. I wrote this out ahead of time so I wouldn't make mistakes, and guess what? I'm not perfect. All right? Now, if we move over to Chapter 8 now, all we do is we replace the v with omega. So here it was v, now it's going to become omega. The original velocity, v sub 0, that would become omega sub 0, or omega sub o if you want to call it o. And the acceleration, linear acceleration a, now becomes alpha, the angular acceleration. So the same equations we had in Chapter 2 are very similar to the ones we have in Chapter 8. Here, distance, the angle in radians, original velocity, the acceleration, and down here, this one, v squared, v sub 0 squared, 2a, x minus x sub 0, and this becomes omega squared equals omega sub 0 squared plus 2 alpha theta sub minus theta sub 0. Now I think it had enough to absorb with this one, so we're going to shut this off and then we'll move on to another part of the video.